Okay, the second problem involves a system where the center of mass is, well, I'm sorry, where your new coordinate system is moving not just in the x direction, but in some direction within the plane. Okay, so it's not moving in a direction that's parallel to the lines of motion of the two objects. And you want to think about what the collision is going to look like from that system. Okay, we'll talk about that next time, hopefully. Maybe I'll do a video on it. But right now we want to move on to the third problem, where we make an important point about rotational systems. Now, you observed rotational systems in lab last time. We have a rotational system whose initial angular velocity, the rate at which it's sweeping out angle, we have a beam rotating, sweeping out angle at a rate of 5 radians per second. Now you right now probably ought to think, what's 5 radians? How much is that? How fast is that thing moving? If that beam is a few meters long, made out of steel, do I need to get out of its way, or can I just, stop with my hand? Can I just let my head stop it? I didn't draw this picture in class because I wanted to drag it out of you, but how much is 5 radians? Now, nobody knows the definition of a radian, and I'll confess I didn't know it either, because in prerequisite courses you're usually given formulas to memorize, formulas that nobody in their right mind would ever memorize, because they can't be retained by anybody with anything resembling a non-extraordinary photographic type memory. Okay? Too confusing. There's a very simple definition, and it's obvious that everybody has been fed formulas rather than understanding. Now, the understanding is, maybe a little subtle, but it's not that bad. A radian is just the angle where the radius, which could be the length of this segment or the length of this segment, is equal to the distance along the arc. So 1 radian, the arc distance, equals the radius. And you don't want to do calculus or physics really with any unit of angle if you're talking about rotating objects and so forth, or if you're talking about the calculus of trigonometry. You don't want your angles to be measured in anything but radians, because if they're measured in radians, you don't have to carry a lot of conversion factors around with you. If they aren't measured in radians, you do have to carry them around, and they totally confuse the issue. Also, they obscure the elegant meaning of the radian. Okay? Arc distance equal to radius. Okay, so 5 radians per second means what? Well, it means you go 5 of these in a second. 5 of these would carry around to maybe about here, so it's about 1001. You're going around about this fast. If it's a beam, it's rotating. I don't know if I can rotate it through that angle. It's rotating about this fast. Okay? So, that's what you're talking about. Now you're talking about that beam slowing to velocity 0, angular velocity 0, in 4 seconds. You're given that the graph of omega, of angular velocity versus time, is a straight line. Okay, angular velocity isn't represented by the letter V. It's also not represented by the letter W. It's represented by something that looks a little bit like a W, but a W has a couple of points down here at the bottom. This one doesn't have any points. It's rounded at the bottom, and its name is omega, and it's a Greek letter, and you need to use that Greek letter, and I don't want to see anybody using W where they should be using omega. You can't type omega if you're working in HTML, you can code it easily enough. Ampersand OMEGA semicolon, that codes it. But you want to type it out. Okay, if you're typing. If you're writing, you write it like this. You don't write it as a W. Okay? On a graph of omega versus t, if the graph is a straight line, there are two possibilities. One possibility is you have a straight line with positive slope. Another is you have a straight line with negative slope, and of course you could have zero slope. You really can't have a vertical straight line. That would imply an infinite acceleration. It would take infinite forces, torques, and so forth. Okay. So from the information you're given, you're told that it slows from 5 radians per second to rest in 4 seconds. So the first question is, what's the rate at which the angular velocity changes? I've got a smudge there. I'm going to fix that while I'm talking. Okay, at what rate does the angular velocity change with respect to time? Well, the rate at which one quantity changes with respect to another is the change in this quantity divided by the change in that quantity. The rate of change of angular velocity with respect to time is change in angular velocity divided by change in clock time. Okay. So, for the interval you're given, it takes 4 seconds to come to rest. Now here is a picture of a part of the graph that might represent that. You have 5 radians per second at this instant, and you have a 4-second interval before it comes to rest. So what is the average rate of change of your angular velocity with respect to time? Well, that's change in angular velocity divided by change in clock time, which is going to be negative 5 radians per second. If you're at 5 radians per second, you're going to have to lose 5 radians per second to get down to rest to 0 radians per second. Divided by 4 seconds, that's negative 1.25 radians per second squared. Okay, now what might we call this? If omega is angular velocity, well, by analogy with what you should know, you don't know it as well as I want you to, but by the time we get done reasoning this out, you'll know it all. Okay, by the time we get done working through the ideas of angular velocity and angular acceleration and so forth, you'll come to the conclusion that, well, a change in velocity divided by change in time is an average acceleration. So a change in angular velocity divided by a change in clock time is going to be an average angular acceleration. So this is an average angular acceleration. A little hard to write that, alpha. Okay, that's the Greek letter alpha. Put a bar over it because it's an average. If we do a delta omega over delta t, equals negative 1.25 radians per second squared. And I might have earlier not said the second squared. I'm not sure. Okay, this is average angular acceleration. Now, if we're told that the graph is a straight line, that means the angular acceleration is constant. So straight line graph implies constant slope, constant rate of change. So we can write just plain old alpha equals negative 1.25 radians per second squared. Already you should be seeing that there's a close relationship between the reasoning that we do for angular velocities and angular accelerations and what we do for velocities and accelerations, because this is identical to the sequence of reasoning and the appearance of the graphs that we used when learning about uniformly accelerated motion along a straight line. Okay? Okay, well, the analogy is so strong, every bit of reasoning that we used in deriving the equations of uniformly accelerated motion and integrating uniformly, integrating the motion equations, whether uniformly accelerated or not. Every bit of that reasoning works exactly the same for rotation. Everything you reasoned out about uniformly accelerated motion along a straight line applies to acceleration, and all you have to do is replace velocity with angular velocity, acceleration with angular acceleration, and position with angular position theta. Now your angular position theta, if something keeps going around and around and around, theta keeps increasing. It doesn't go around until the angular position is 2 pi and then goes back to angular position 0 and then goes from 0 to 2 pi again and from 0 to 2 pi again. The angular position keeps increasing. So if you go around the circle 3 times, you've gone through 2 pi radians each time. You will have gone through 6 pi radians. So theta is a function of t, x is a function of t, and we might as well make that explicit. A little crowded on the V there, but you should understand what I've written. So that you can actually take the equations of uniformly accelerated motion and translate them into equations of uniformly accelerated angular motion. Just replace your x's, v's, and a's with thetas, omegas, and alphas, but know what they mean. And you do want to use these symbols. When you're reasoning out angular velocity and angular quantities, the reasoning is identical to the reasoning you're used to. You're going to want to use the symbols you're used to. Don't do it. There's a difference. There are important differences between between the physics of rotating objects and the physics of objects moving along a straight line, translating along a straight line. Okay? You want to get used to the angular notation because it's going to be used with some kind of different symbols when we start talking about angular momentum and angular kinetic energy and some of the other things that are associated with angular motion. Right now in the chapter you're moving into, it's just analysis of angular motion, and it's completely analogous to the analysis of linear motion. But be sure you use the angular symbols, the symbols for angular motion.